Today we're going to learn how to do linear regression on the TI-83 Plus calculator. I'm going to be using the data found in the linear regression example point file that's available on our website. The first thing you should do is enter the data into your calculator. I've done this already. As you can see, if you need help entering data into your calculator, then look for the appropriate video file that's found on our website. The next thing we're going to do is decide which variable should be the independent variable and which should be the dependent variable. The independent variable is the size of the television, and that is the variable that we're using to make a prediction. The dependent variable is the cost of the television, and that is the variable that we are predicting. We're going to make a scatter plot of this data. The way you make a scatter plot is you press second and stat plot, and then move to plot 1 and move over, press enter, and then select on, and then down at type it should be the scatter plot should be selected. X list and Y list should be the two lists of your data, and the mark, you can choose either the little box, the little plus sign, or the dot. When you get done with that, you can press zoom and then go down to zoom stat and press enter. And here's my data. Next, looking at this data, it does look like there is a relationship between the variables. The price of the television does increase as the size of the television increases. On this plot, the size of the television is found along the x-axis, which is the horizontal axis, and the price is the y-axis, which is the vertical axis. Each of these dots is a different television from the data set that is provided to you. The next step is to calculate the least squares regression line. To do that, you press stat and then go over to tests, and then at the very bottom you'll find linreg t-test. Press enter. Make sure that the X list is the list that you entered your television size data, and the Y list is the price data. Frequency, leave at 1. The beta and rho, that's that funny looking B and the funny looking P, leave that as not equal to 0. And down here at reg EQ, we're going to select vars and go over to Y vars, select function, and choose Y1. Before we started, I made sure that my Y1 variable was empty. If yours is not empty, if it has an equation, then you'll get an error when at the next step. What you'll need to do is clear out that Y1 variable. But once that's done, you can press calculate, press enter, and we get a bunch of information. The first thing you'll notice is a t-value and a p-value. The p-value refers to the hypothesis test that this has a significant relationship between these two variables. And in this case, since this is such a small p-value, the conclusion would be that there is evidence to suggest that a relationship exists. Scrolling down, you can see A and B. Those refer to the coefficients in the linear regression model. A is the y-intercept and B is the slope for this model. There's the standard error for the estimate. We'll be using that to build a 95% confidence interval for the line of best fit. R value is the correlation coefficient, and the r-squared value is the coefficient of determination. Now, if you did enter y1 or some y value for the linear regression line, you'll find that in the y equals menu, you will have the line of best fit. And then when we graph the data again with the line of best fit, you'll see the line of best fit on the graph. We will now set up the 95% confidence interval for this line of best fit to see if there are any outliers. So going back to our main menu, you'll notice that the standard error for the estimate is 268.35. Going back to the y equals menu, I set up the two pieces of this 95% confidence interval by adding and subtracting two standard error for the estimates from my line of best fit. To do that, I move down to y2 and then press vars, yvars, function, y1, and then add 268 times 2, and do the same thing for y3, except that I'm going to subtract. Whoops. Yvars, y1, minus the standard error for the estimate times 2. That'll give us a rough idea of a 95% confidence interval for any estimate made with the linear regression line. Now we can graph this. There. You see that the bars represent a 95% confidence for any estimate made with the linear regression line. Any of our points that fall outside these two bars or lines would be considered an outlier. There aren't any for this graph. Next, we'll take a look at the correlation coefficient. Quit the graphing menu. The correlation coefficient is 0.941, and that is a significant correlation coefficient based on the p-value that we can't get back up to, but it was a significant p-value. The next step is to find an estimated sale price for a couple of televisions. The first one is a 32-inch television. To find that estimated sale price, we'll use this linear regression model, y equals a plus bx, and use 32 for x. X represents the size of the television, and y represents the price of the television. Since I've already entered the linear regression model into the y equals menu, it's pretty easy to get this. To do this, you press vars, press vars, go over to yvars, and if you remember, I had my linear regression model in y1. So select y1, and then enter 32. Oops. And then press enter. And this is the predicted price of a 32-inch television based on the data. Next, we'll find the cost for a 50-inch television. And we do this the same way. Press vars, go over to yvars, select y1, and then enter 50. $50. And the predicted price for a 50-inch television is $1,006.44 rounded. If we were to plot this line by hand, we could use those 2 points on a graph to plot the line of best fit. We've already plotted the line of best fit using our calculator. Finally, there's a few questions about the line of best fit. Let's go back to the graph. One question is, does it appear that a line is the best way to fit the data? Why or why not? You might notice that this data appears to follow a curve. That is, it's pretty shallow. The slope is pretty shallow here at the bottom end of the data for smaller televisions, and then it gets steeper at the upper end. And so I suspect that a better fit would be with a curve, maybe a parabola or a quadratic curve. And the reason is that it does seem to be less steep here at the bottom end and more steep up here at the top end. Finally, there are questions about the outliers, and there aren't any outliers. This point up here is very close to the line. It's on the line almost, but it's not quite an outlier. Finally, we want to know the slope of the least squares line, and we want to interpret that slope. So let's quit this once more. And I guess I'll go back to my y equals menu. The slope of the line of best fit was 29.67. And you can view that as being a representation of how much the independent variable, how much the dependent variable will change for every increment of the independent variable. So in the case of this television example, 29.67 is the additional cost for every inch of television screen based on this model. So if I increase my television screen by 1 inch, I'll be paying $29.67 more for that television.